Okay, so let's examine the gain in more detail for the common source amplifier with the diode load. Now we know that the voltage gain for all amplifiers has the form of minus big GM times R total. In this case, we're going to say the resistance at node A. We know that big GM is just equal to GM1 for this particular amplifier. And by inspection, we can show that RA is equal to 1 over GM2 in parallel with RO1. Now, we're further going to simplify this as we noted before and note that 1 over GM should be much smaller than RO. And so we're going to approximate this as just equal to 1 over GM2. All right, so let's rewrite our gain. And we can say that AV is equal to minus GM1 over GM2. Or we can write this in the form of 2 mu n C ox W over L ID W over L 1 divided by square root of 2 mu n C ox W over L 2 times ID. Now here we can see that the voltage gain is proportional to square root of W over L1 over square root of W over L2. So if we want a big voltage gain, this tells us W over L1 needs to be much, much bigger than W over L2. In other words, we need to make that diode connected device very small. But we also know that geometrically we're not going to make the transistors be able to be too different in size. So this is not a good option if we want large gain. Okay, so what can we do? Well, let's go back and reinvestigate that PMOS current source. Okay, so here we again know that we have that gain that's of the form minus GM times RA, where we're finding the total resistance at node A here. This means that we're going to find the resistance looking up into the source of the PMOS and down into the drain of the PMOS and down into the drain of the NMOS. Big GM is again equal to GM1, and R sub A is equal to RO1 in parallel with RO2. In other words, the resistance of the NMOS in parallel with the resistance of the PMOS. So we can say that our voltage gain is equal to minus GM1 times RO1 in parallel with RO2. Now we know that this is a very big gain. It's in fact close to the intrinsic gain of the device. But we also note that we're going to have to produce a bias voltage, VB. We're going to learn how to produce that bias voltage in the next class, but just know that this is the complication. We get a very large gain with this circuit, and the PMOS transistor is acting nearly like an ideal current source, but we have to produce a bias voltage in order to realize it. Now, one more thing that I want to mention is that we can use what's called a Cascode amplifier, and this is where we stack a common gate amplifier on top of a common source amplifier. If we look down at the load resistance, looking into the drain of the upper device, we would find that our load is equal to RO2 times 1 plus GM2 times RO1. Now we get this from the inspection analysis sheet, where the resistance looking down in the source of the upper transistor is the RO1, and that's how this formula arises. Now, oftentimes, we approximate the resistance looking into the drain of a Cascode transistor as GM times RO squared, assuming that if the devices are roughly equal size and that the product GM times RO is much bigger than 1, we can make this approximation. Now, it's really important to note that this is a very big resistance. And so this is going to be very useful to make high gain amplifiers. But what's the drawback? Well, we now have 2 transistors that need to be saturated, so we need a higher voltage at the drain to keep both transistors saturated. And as we noted for that PMOS-based current source, we also have this VB that we're going to have to generate somehow, and we'll need a bias generation circuit for that. So we'll go ahead and stop there for the day, and we will pick it up in the next lectures that will talk about how we're going to generate those bias voltages.